Hello, everybody, and welcome back to your channel of Math and Engineering Made Easy. If you remember last time, we had a session on Green's theorem, and we were talking about how Green's theorem transforms a line integral into a double integral, because Green's theorem works only in 2D. If you want to work in 3D, we are going later to cover Stokes' theorem, uh, which works for, it's an extension of Green's theorem for 3D. Last time we said that this is the form that's basically, in fact, we prefer to write it as f dot t ds. Why? Because if you think about it, if you are talking about a circulation around a closed curve, whether this curve is a triangle or a circle or a parabola, it doesn't matter. But you only want to see the amount of flow that goes along the periphery. So you always do a dot product with the tangent because the tangent gives you the direction of motion, right? So when you do the dot, if you remember, it's a projection. We are projecting the field or the vector field onto the direction of motion. But when you want to calculate the flux or the divergence going out, you want to have something perpendicular to the tangent. So when you do the dot product, you get zero circulation. Everything is talking about divergence or flux. In which case, so the second way we can do that is to say it's the line integral of f dot n, with while n is the perpendicular, it's a unit vector normal to the trajectory, right? Not tangential to it. And if you do this, remember when you do the dot product, when you calculate the divergence, remember del dot f. So you get, if this is m and this is n, you take the partial x of m and partial y of n. That's a dot product. You multiply the x components together, the y components together, and then you add them up. So it becomes m dx, or we call it mx plus ny double integral over the region dx dy or dA. So all what we change really is that instead of saying ny minus mx, we say, I'm sorry, nx minus my, here we say mx plus ny, because that's a dot product, that's a cross product. There is nothing, like magical about that. It's just here you do a dot product, here you do a dot with a tangent or a cross product to get the curve itself, right? Perpendicular to that, so you do the cross product. So there is nothing really other than that. Let's take a couple of examples. I prepared 3 examples again like last time, but this time we are going to use the flux. So they give you a velocity vector field as that, and the closed curve is a rectangle, and we always assume counterclockwise. And as I said, if you do clockwise, it's just the same answer with the negative sign. This is 0, 2. This is 4, 2. This is 4, 5. And this is 0, 5. Okay, so let's do the work. Let's calculate mx. Mx is the partial derivative of m with respect to x, so you get 5, just a constant. When you do partial n, this is partial m, partial x, so we call it m sub x. I'm just in the beginning, I'm showing you 2 different ways of calling these, but eventually we are going to use an abbreviation so we don't waste time. Say mx plus ny. Ny here is 3. Wow, so mx plus ny is 8. Notice 8 is a constant. So do I need a double integral here? So the flux equals 8 times the area of the rectangle. 8 times the area is base is 4 from 0 to 4. Height is 5 minus 2 or 3. 3 times 4 is 12, times 8 is 96. This is meter per second. That would be a square meter per second. That's the flux. That's the amount of water that is leaving that rectangle if that's the velocity vector. Okay? Leaving meaning positive. Going into means negative. Alrighty, so the first one was very quick. Let's look at the second one. The second one is similar. They give you that, and they say, but C is a circle with radius 2 centered at the origin. And again, it's positive, meaning counterclockwise, like we did before. Oh, I picked a bad problem, right? Because again, mx and ny are constants. Okay. So it will be a short video. That's the good part for you. Mx is 4, ny is 5. So when you add them, you get 9. And since it's a constant, then the flux equals 9 times the area of the circle. The circle has a radius 2. So the area is 2 square pi, meaning 4 pi times 9 is 36 pi. Wow. I didn't notice that. That was an easy one. Okay, let's take the last one then. The last one will not give you a constant. Good. So this is the m, this is the n. And when we do the integral, we are going to take mx is 3x squared and y is 3y squared. So we add them up, remember? So that's what we get. So we will get the flux will be a double integral over the region, which is the circle, of 3x squared plus 3y squared dx dy. Every time you see x squared and y squared, think what? Think what? Circle, ellipse, parabola, or ellipse, hyperbola. What should we go and think about? Polar coordinates. Yep, polar coordinates. So we are going to say x, it's a unit circle, so the radius is 1. So we're going to say cos theta, and y is sine theta. And dx dy, remember, is r dr d theta. So when I take this integral, I'm going to say equals a double integral. I have a 3 as a constant, x squared plus y squared. You already know that x squared plus y squared equals cos squared theta plus sine squared theta equals 1. So you get 1 times r dr d theta. R goes from 0 to 1. Theta goes from 0 to 2 pi. And again, that's really a very simple one. Notice that the r and the theta are independent, so I can rewrite that as 3 integral from 0 to 1 r dr times integral from 0 to 2 pi d theta, right? Because when I integrate each portion, it doesn't contain, the integral of r doesn't contain theta, and the integral of theta does. So we can do it very fast. We can say r squared over 2 from 0 to 1 times theta 0 to 2 pi. Notice because these are zeros, I don't care about them. I say 3 times 1 square over 2 times 2 theta. So the 2 and the 2 cancel, and you get 3 pi, and again, a very short and simple integral because, again, we end up almost with a constant. It's just r. So when you integrate it, you get r squared over 2, and the rest is history. You just multiply them together and simplify. Okay, so that was really a short video, but it shows you that Green's theorem can calculate the circulation around a closed curve or also the flux through that closed and simple curve. Okay, I hope this was also another easy one. Maybe we'll start talking about surface integrals after that and later, because we will need it when we do Stokes' theorem. And that will probably conclude this part of the sessions. Okay, thank you very much for your time. And again, write me comments if you need anything or if something is unclear, if I made a math mistake. Or if you have any general question, and I'll try to get back to you as soon as I can. Thank you very much for your time. Hope to see you soon. Good night.